Hey folks, we're going to do an example using Gauss's law and conductors. And let me explain what you're looking at, and then when you need time, go ahead and pause the video and write all this stuff down. So what you have over here, and you want to draw this picture pretty big in your notes, you have three concentric spherical metal conductors. You have a solid metal ball in the center here, has a radius little a. You then have a metal shell that has an inner radius B and an outer radius C. And then you have another metal shell, inner radius D, outer radius E. On these pieces of metal, we've put a positive 2Q charge on the central ball, a positive 3Q charge on the middle shell, and a negative 1Q charge on the outer shell. Q could be anything. Maybe it's a nanocoulomb or something like that. So this could be positive 2 nanocoulombs, positive 3 nanocoulombs, and minus 1 nanocoulombs. What we're going to do is we're going to determine the electric field at all these locations. There's actually one more down here, R bigger than E, outside the whole thing. So we're going to determine the electric field at basically every location, the charge on each surface, and the surface charge density at each surface. Okay, so if you need a moment to pause the video and kind of copy all this down really well, go ahead and do that. All right, hopefully you're back. Okay, so what I'm going to start with is I'm going to kind of go back and forth, but I'm going to start with the electric field. Okay, I know that within a conductor, the electric field has to be zero when we've achieved electrostatic equilibrium. So therefore, when I'm inside this metal ball, R less than A, E is going to be zero. And I'll make a little line here to separate these. Also between B and C, the electric field has to be zero. And also between D and E, the electric field has to be zero. Because in all three of those locations, I'm within a piece of metal, and the electric field within a piece of metal, it's in electrostatic equilibrium, has to be zero. Okay. Now, what about the other places? Well, here's where I'm going to go ahead and figure out the charge in different spots. So for our first part of this, within the solid metal ball in the center, there's no charge because the field in there is zero. So all this positive 2Q has to go to the outer edge of that ball. Okay, now for this 3Q, how much charge has to be on the inner surface at B, surface B? Okay, well, here's how you do this. I know that within this spherical conducting shell here, between B and C, I know the electric field is zero. And if I imagine drawing a sphere that's concentric with the inner and outer part of that, between B and C somewhere, I know that the electric field here is zero. Therefore, all the charge within this dashed sphere that I've just drawn part of, the total charge within there has to be zero because the field within that area is zero. And remember, Gauss's law says Q in over epsilon naught equals double integral E dot dA. So if E is zero, then Q in must be zero. So how do I make, within this kind of blue sphere that I've drawn part of here, how do I make the charge inside of that blue sphere equal to zero? Well, I have to put a negative 2Q here because that's got to cancel out that positive 2Q on the inner ball. So the charge at B is negative 2Q. So the total inside that blue sphere that I've traced part of has to be zero. Now, how about the outer part? Well, the total charge on the middle shell is 3Q. So negative 2Q plus what gives you 3Q? Well, that's positive 5Q. So this has to be positive 5Q. Now, looking at the outer shell here, I know that the field at the spot where I'm drawing my dash line right now, that's part of another spherical shell, the field there is zero. So the total charge inside has to be zero of that sphere. So how much charge do I got to put on the inside of this thing? Well, negative 5Q. So now all four of those cancel, so I have no net charge inside of this blue sphere I've drawn. And then if the total charge on the outer shell is negative 1q, negative 5q plus what equals negative 1q? Well, that's positive 4q. So that's so on surface D, we have a negative 5 and a q, and here we have a positive 4 and a q. Okay. Now, a couple things to notice pattern-wise. First of all, hopefully you see a pattern. These come in pairs: positive 2q, negative 2q, positive 5q, negative 5q. So that's one pattern you see. The other pattern is, what's the net charge on the entire system? Well, you got a 2 plus 3 minus 1. That's a 4. The outer shell will have the overall net charge of your system. So that's another pattern to notice. Now, what about the electric fields, like here, for instance? Between A and B, so that's like here. Well, imagine I drew a Gaussian sphere there. Well, how much charge is inside of that? Well, B2q. And it's a spherical charge, so it's going to behave like a point charge. So my field there would be K times 2q over r squared. And if I look between C and D, that's here. Okay, how much total charge would be inside of that sphere? Well, it'd be a 3q plus a 2q. That's a 5q. So this would be K times 5q over r squared. And how about outside this whole thing? Well, how much total charge, so if I'm out here somewhere, how much total charge is in the system? Well, it's 4 times q. So you'd have K times 4 times q over r squared. Okay, so there's your electric fields. Now, for your charge densities, that's really easy. You're just taking whatever charge is here and dividing it by the surface area. So this would be 2q over, what's the area of the sphere with radius a? Well, it's 4 pi a squared, and that'd be positive. For b, it'd be negative 2q over 4 pi b squared. For c, it'd be positive 5q over 4 pi c squared, etc. Okay, I don't even think we have to write D and E out. It'd be the same kind of pattern. Okay. So now I got one more thing to add, but before I do that, so again, look for patterns. You know, I started with, hey, I know the electric field is 0 within a conductor. I start with that, and from that, everything else flows. Okay, so for instance, I know that everything above that line has to add up to 0q, and everything above that line has to add up to 0q. In other words, everything within this sphere has to add up to 0, and everything within this sphere has to add up to 0. Because Gauss's law says double integral E dot dA equals Qn over epsilon naught. Well, if I know this is 0, then this has to be 0, right? So if I look at this part right there, let's say, I know the electric field there has to be 0 because it's in a conductor. Therefore, I know all the charge inside of that point has to equal 0. Now, one last thing I'll mention. Let's say you take this whole thing and then you ground it. You connect it to ground. What's going to happen? Okay. Well, this is a metal conductor. It's a wire. Okay. So charge will flow until the electric field out here is 0. Well, how do you do that? Well, you have a negative 4q flow in and neutralize this. Okay. So what would end up happening is the outer shell would then become a 0q charge. And then you'd have no electric field outside of this thing. And then your total charge on your system would be 0. You'd have a positive and negative 2q, and you'd have a positive and negative 5q, and all those would cancel, and your net charge would be 0. So if you ground something, the outside charge, assuming there's nothing else going on in the system, the outside charge will become 0. And then therefore the net charge on your system becomes 0. All right, I hope that example was helpful, and thank you very much.